All right, my friends, let's take a look. So for, I think I'm going to go ahead and do this a little bit backwards today. Let's talk about the formula for the distance between 2 points on an XY plane. For some reason, I think it's the way our geometry textbook works for the one we have here at Camas High School. For some reason, I get students who are not very familiar with this formula, and so they have a tendency to use Pythagorean theorem instead, and there's nothing wrong with that, but let's make sure that you understand why the formula makes total sense. So let's say you have, a point x1, y1, and another point x2, y2, and you're trying to find the distance, between those 2 points. Let's say that you did use the Pythagorean theorem. Well, you would find the lengths of the legs of this right triangle. So I hope it makes sense that the length of this longer leg here at the bottom would simply be x2 take away x1. And then the length of the shorter leg here would simply be y2 take away y1. So if you use Pythagorean theorem on this right triangle, it would say d squared, which is your hypotenuse squared, would equal the length of one of the legs squared, let's say this, plus the length of the other leg squared. There we go. And then last thing you could do to really derive this distance formula would be to square root both sides. There we go. So just in case you've never seen the derivation of the distance formula for 2 points in the XY plane, there it is. Anyway, so if I was to use this formula to do part 1 here, then I would simply take the square root of, the difference between the x coordinates. You could do 2 minus 6 or 6 minus 2. Kind of can't mess this up because you're going to square it anyway, so you get the same answer. And then you could do 10 minus 5 or 5 minus 2. Or sorry, 10 minus 5 or 5 minus 10, that is. Either way, you're going to square it anyway, so it ended up being fine. And so you'd end up with 3 squared plus, looks like 5 squared, which is a square root of 9 plus 25. So it looks like we're getting the square root of 34 for that distance there. And then we could just say units. You, of course, could have used the Pythagorean theorem as well, but I did want to make sure you're as comfortable with this distance formula down here as you can possibly be before we start this lesson. So hopefully you feel pretty good about that. Okay, and why do you need to be comfortable with that distance formula? Well, let's talk about the concept of the day here. Okay, let's see. Here we go. Okay, so here's the concept of the day. We're going to talk about arc length of a smooth curve in an XY plane. So let's say you have a graph here. And you have some nice continuous function here, nice smooth continuous function, and you are asked what the arc length is on a given interval. Okay, so first let's talk about what is meant by arc length, okay? So the arc length of this function f on an interval would be, so let's use your imagination really quick. It would be, imagine that you take some string and you put one end of the string at the point A, F of A, and then you kind of press the string down to follow the path of this curve until you get to the point B, F of B. So you have the string following the path of this curve, and then you cut the other end of it at the point B, F of B, and then you straighten it out and you measure it. So that would be the arc length of this function f on the interval from A to B. So now let's talk about how are we going to find such a length? How are we going to do it? Well, the distance formula would help us find, the length of straight segments. So what if we just did the distance formula a lot of times? Let's kind of zoom in here. What if we did the distance formula a lot of times? So like, let's say, I don't know, what would a lot be? It would be tedious work, wouldn't it? So what if we did it 1, 2, 3, 4, 5 times? What if I broke the interval from A to B up into 5 subintervals and did the distance formula 5 times? What would I have? I claim that I would have a very decent approximation of the length of this curve. I would have a very decent approximation of this arc length. Well, how many times would I need to do that to get a perfect value for this arc length? And since we're calculus students, it's probably becoming a little bit easier to basically say, you know what, you would have to break the interval from A to B up into infinitely many, infinitely thin subintervals. And then you could do the distance formula infinitely many times. And so get to work. Anyway, so yes, you will see an integral play a role here, and we'll make sure that we put the correct distance formula inside the integral. So the integral will add up infinitely many, infinitely small little lengths of segments, and hence will give us the perfect arc length. Okay, so let's talk about what we're going to put into the integral. So there will be some algebra involved here, so hopefully you're okay with that. Okay, so let's focus on just one of these segments for starters. All right, my friends, let's say that we are going to focus on this part, this segment right here, this first little segment, okay? But let's use your imagination and pretend that that segment is infinitely small. It's an itty bitty tiny little segment. So this distance right here, known as the change in your x coordinates, if you're using the distance formula, it would be x2 minus x1. And then this distance right here, if you're using the distance formula, would be known as y2 minus y1. Now, if this was an infinitely small segment, then as the number of little segments, approaches infinity, this gets infinitely small. And so x2 minus x1 would become an infinitely small change in x. And y2 minus y1 would become an infinitely small change in y. And so in that case, then, we could say that this distance right here could be thought of, assuming that we've let the number of little subpartitions between A and B approach infinity, then that little distance would become very, very small. And so it would be, its length could be described as the change in x squared plus the change in y squared, like that. There we go. Now, what I'm about to do is just kind of use a little bit of algebra manipulation to make the format look a little different, so it'll make sense and when we move to the next step. So for starters, I'm going to take this square root and multiply it by a creative version of 1. And here's my creative version of 1. I'm going to multiply by dx over dx. And then, just to be a little more manipulative, I am going to split the dx over dx by leaving the dx that's on the top there where it is. I'm going to copy the square root function as is. And then this little dx that's on the bottom, I'm going to write it over here as 1 over dx. There we go. Now I'm going to take 1 over dx and I'm going to put it back underneath the square root. Well, think about, what would it go back under the square root as? What would it have been if it came out as 1 over dx? And it would have been under there as 1 over dx squared. I hope that makes sense. I'm just going to copy the rest of the radicand as it is. There we go. Next step, and it's okay if you're not sure where I'm going with this, just as long as the steps make sense as we go. Next step is going to be to distribute 1 over dx squared in. And what do you think we get when we multiply 1 over dx squared times dx squared? That's right, we get 1. And then I hope it makes sense. When you multiply 1 over dx squared into dy squared, you basically get dy dx quantity squared. And then you've got this dx over here at the end. There we go. Now let's take a minute, just in case you've gotten lost in what we're even doing here. Let's go back to the master plan. This is an expression for one of the infinitely many little segments that we're going to need to add up. How are we going to get the arc length of this function f on the interval from a to b? We're just going to need to add up infinitely many, infinitely thin of those, or infinitely many, infinitely small of those. So here's the arc length formula. They use lowercase s for some reason to represent arc length. So we are going to add up infinitely many of these guys. And you could write dy dx, but another name for dy dx is f prime of x. And we would start adding at A and stop adding at B. There we go. I hope that makes sense. Now, this formula is for finding the arc length of a given function f on the interval from A to B. And it's great as long as you're given something that is a function of x. So I want you to think about, what are you going to do if you're given something that is not a function of x, as in it doesn't pass the vertical line test? So it's not a function of x, but it is a function of y. Here, I'll give you a hint. Let's say you're asked to find the arc length from a to b, where a and b are y values, of this function of y on the interval, so on this interval from a to b. How would you find that arc length? The arc length would be the integral from a to b of the square root of 1 plus, and instead of f prime of x, you probably guessed it, f prime of y. There we go. All right, my friends, take a moment and memorize the arc length formulas that you see here. And make sure, even if you need to pause the video, that you do take a second and memorize them before you start example 1. All right, with that said, I'll trust that you do the right thing. And here's example 1. Find the arc length of the graph of each function over each indicated interval. See how it goes. Check in with me in the next video. Good luck.